Hello, everyone. My name is Damien Desfontaines. I work at a small startup called Tamlet Labs, but today I'm here to present work we did at Google with my colleagues James, Bryant, and Chinmoy on differentially private partition selection. So first, what is partition selection? Let's take a simple example. Imagine that you have a log of interactions with an online service. Some user identifiers, some time, as well as a device type. Here, the device type could be really anything. Think of it maybe as a user agent string. You don't know in advance what are the possible user agents that you're going to see in your data. Here, for example, we have a laptop, a phone, a desktop computer, a watch, and then a crystal ball for some weird reason. If you want to count how many people you've seen with a single device, given a specific device, you are going to do something like this in SQL. You group by device model. And for each device model that you see in the data, you count the number of identifiers. Okay, so when you do that, you end up with a histogram. And the question is, how do you make this histogram differentially private? Well, we all know that differential privacy requires the addition of noise. First off, let's try and add noise to the data. Is this enough to achieve differential privacy? Turns out, not so much. Imagine that you have a single person in your data, here in this greenish color, that's connected to your service with a strange device, let's say a crystal ball here. When you add noise to each of the partitions of the buckets, this, with sort of high probability, this will appear in your data, this specific partition, this crystal ball. Right? You're going to add noise to one and return a statistic associated with this crystal ball at, that corresponds to 1 plus noise. But of course, if you remove that person from the database, then you don't know that this thing exists. When you do a group by, this partition, this bucket, it doesn't exist. So you're only adding noise to the other partitions. And of course, these two situations here end up being very distinguishable. In one case, you're releasing a crystal ball, the partition corresponding to the crystal ball, and in the other, you're not. So this clearly is a problem because differential privacy is supposed to prevent you from distinguishing when you add or remove a user from your database. The typical way we solve this is after adding Laplace noise, we also use a threshold, and we only release the counts that are above the threshold. So here, this can mean that if you have a single person in a specific partition, you're only going to release that partition if the noise 1 plus noise ends up being above the threshold. And we hope that it doesn't happen too much if the threshold is high enough. And it gives us epsilon delta differential privacy, and delta is the probability that this happens, in which case this is the situations are distinguishing, otherwise they're not distinguishing. So this is how you adapt the typical Laplace mechanism for histograms to a situation where you don't know the set of partitions in advance. And you go from epsilon dp to pure differential privacy to epsilon delta dp, approximate dp. Okay, the question that we're asking in this fork is, can we do better? And it turns out, as we've seen, that we are going to do better. Otherwise, I wouldn't be here. Let's start to give you an intuition about how we can do better by plotting the probability of releasing a partition depending on the number of people in the partition. So here, this is simply the cumulative distribution function of the Laplace mechanism that's sort of discretized here. And of course, the more people we have in each partition, the more likely we are to be above the threshold once we add noise, and so the closer we are to probability 1 of releasing that partition. And of course, as we saw here, at 0, if we don't have any record associated with a certain partition in the data, then we have 0 probability of releasing that partition because we don't know that it exists in the first place. So if you take a look at the Laplace mechanism, how do we construct this plots describing the probability of releasing a partition depending on the number of people? We saw that P0 equals 0, and we also saw that P1, so the probability of releasing a partition with a single person in it, is exactly the probability of a catastrophic privacy failure in a way, distinguishing events. So this can only happen with probability delta. And then once we are at 1, to go from 1 to 2, we're multiplying that probability by e to the epsilon. Why are we doing this? It's because the Laplace noise is this double exponential distribution, and it has this nice property, very convenient in differential privacy, that when you add when you go one horizontally, you're multiplying by e to the epsilon vertically because of this nice exponential shape. So of course, to go from P3 to P2, from P2 to P3, we do the same thing. We multiply by e to the epsilon, etc., etc. And then when we're on the other side of the distribution function, we also have the relationship of the same kind, but it's with 1 minus p because we're on the other side of the curve, so the relationship is somewhat reversed. So now that we've seen it, we've seen an interpretation of the Laplace mechanism and thresholding in a somewhat iterative manner. The question is, okay, can we use that iterative intuition to find an optimal shape of that curve here? As we saw earlier, we can't do better than 0 at P0 because we don't know that partition. So this is actually optimal. Similarly, if we are releasing a partition with a single person in it, that's a distinguishing event compared to if we release a partition with 0 people in it. So again, we don't have a choice. The maximum, the highest this curve can possibly be here is delta. But then to go from P1 to P2, before that, we were just using e to the epsilon. But since we are using approximate dp, we have a little bit of budget, a little bit of additional budget delta here. So we can actually compute that probability by saying the maximum probability we can get away with is e to the epsilon plus delta. And when we continue doing this, over time, we're winning, we're increasing a little bit more, the probability of releasing a partition using this sort of optimal mechanism rather than if we use the Laplace mechanism. We continue, we keep going like this. As you see, the more we go, the better it looks. And after some point, we cross the midpoint, and then we also use the same relationship but reversed with a minus delta over there to get the optimal formula. And this gives us, in a sense, an optimal way of deciding whether we're going to publish a partition depending on the number of people in it. So that's really neat. That algorithm I hope that I convince you with this iterative process that this algorithm is optimal. You can't do better than this. So this is great. Now, this iterative way of getting the probability distribution, the probability of releasing a specific partition is a little bit unwieldy because it would require us to, every time we're looking at the number of people in a certain partition, we would need to do this iterative process to figure out what probability to use. So it would be nice if we have a closed form formula for this. Luckily, all the relationship involved here are actually pretty simple. So we can transform that iterative process using math into a closed form formula, which is really neat. We can even do better than this. Not only is there a closed form formula for this mechanism, but we even can prove that this mechanism is actually equivalent, again, using some math, to adding a specific other kind of noise to the data and then thresholding. So instead of adding Laplace noise and thresholding, what we're going to do is we're going to add this kind of weird double geometric that is bounded, bounded double geometric noise, of course, in a discrete version, and that actually corresponds to the exact same thing as the closed form formulas we just saw above. So this is really good news because since we can interpret our mechanism as adding noise to thresholding, along with this interpretation, we can show that the noisy counts, when we add noise to the data and then we use the threshold, just like with the Laplace mechanism, the noisy count, we can publish that. We can actually release the entire histogram, not just the partition. And it's interesting because it means that the optimal mechanism specifically just for the problem of selecting the partition is also the optimal mechanism for the slightly more complicated problem of releasing the entire histogram. So it seems like we completely solved that problem, right? Well, not really. Actually, over the course of this work, we found out really interesting open questions associated with this problem. The main class of open questions is, what if you have more than one contribution per person? Here, we had an implicit assumption that a single person contributed a single partition to the data. And that there's many cases in real life where that's the case, but it also happens very frequently that a single person contributes multiple partitions. For example, let's say a same user logging in through multiple devices. So one of the natural open questions is, can we get some notion of optimality here? Can we find a similarly, maybe iteratively using the same kind of methods, a way of getting an optimal algorithm for this? it's a really hard problem because defining what optimality even means in this context is actually pretty tricky. Because when you have a single partition per user, it's kind of fairly easy. You can reduce the problem to looking at each partition separately. But when each user contributes multiple partitions, then you have to look at the distribution over all users. How many have partitions in common? How is it distributed, etc. And so probably optimality results would require some distributional assumptions there. Finally, another really interesting question is, when you have a lot of contributions per user, typically more than 5, instead of using Laplace noise, it becomes very quickly nicer to use Gaussian noise plus thresholding. You can have this sort of methods that do a little bit better than Gaussian noise by, for example, if somebody hasn't spent all of their sensitivity, we make their contributions weigh a little bit more. But if you want to do algorithms that scale, we're still at a point where the naive algorithm, so somewhat of a naive algorithm, is the best thing we know. There are smarter algorithms that check for each user which partitions were contributed by people before that specific user and decide which partition to contribute to, adaptively like this. But the problem with this is that it doesn't quite scale well because you have to go one user after one user and remember the contribution of every single user before. So if that histogram is very large, if that list of partitions we've already seen is very large, it might not fit in memory. So it's a really interesting problem. I think that, and I encourage you to sort of work on it if that sounds interesting, to try to see if you can do better than this, in a way that scales better. That's all I have for you today. Thanks for listening. I hope this was somewhat easy to understand, and I will be happy to take your questions.